All right, so let's go over everyone's favorite form, and that, of course, is the intermolecular, the IMF attractions form. So we've got these molecules that we're looking at. I'm giving you the shape, and I'm asking you some questions. So the first question is, which of the following molecules experience LDFs? Okay, please use LDFs. And LDFs are these momentary dipoles that are made by the shifting of electron clouds. So the question is, which of the following experience LDFs amongst themselves? Well, my friends, in chemistry, all of them, don't click the none, because all of these right here are molecules, and molecules, all of these have electron clouds. Remember, protons in the nucleus, electrons on the outside. So all of these, of course, have LDFs, whether you're polar or nonpolar. Okay, very important. Number two, which of the following molecules experiences dipolar forces? Okay, so they must be polar. Okay, so clearly the polar ones. Okay, let's see if we can color coordinate to our heart's content. So our polar ones are going to have some asymmetry. This is a little bit polar, but not by much. This is more polar. And one way to know if something's polar or not, of course, is the asymmetry. But if you're looking at dipolar forces, the strength of the positive and negative end, dipole moments are normally given to make that determination. This is polar as well, and this has some polarity as well. So these four are the polar ones. Okay, these are hydrocarbons, and even if they weren't hydrocarbons, because of their symmetry, they would be very, very nonpolar because they have an equal distribution of electrons. These do not. Okay, so that's pretty straightforward. So the methylpropyl ether, all right, and all the way down or have dipolar forces. But the key here is they have dipolar forces and LDFs, okay? Like they have an additional, okay, attractive force because of their polarity. Which of the following molecule experiences London forces, dipolar forces, and hydrogen bonding? Well, if you have hydrogen bonding, you are polar and you have a cloud of electrons. So if we look at our diagram, who experiences H bonding? Now it sounds like it's bonding, but these are again attractive forces. So in order to have H bonding, you have to have an electron deficient H. Okay, and the only one here that has an electron deficient H is 2-pentanol. What? What about 2-pentanethiol? Well, this sulfur atom, as I talked about before, okay, isn't electronegative enough. We have Pon with H bonding. Yes. So when an H is bonded, okay, to these three elements only, do we create a scenario where the electron pair are held so closely to these very electronegative atoms that what's really being dangled out here is a positive proton? We call these electron deficient H's, and only fluorine, oxygen, and nitrogen have a high enough Z for the smallest n possible. All that creates is high electronegativity that can pull this pair so close. So here's fluorine, here's hydrogen. This pair is held so close, this hydrogen is just a little proton sticking out there, and tiny protons have high coulombic charges because you're putting a what? A particle smaller than a nucleus, so much smaller than an atom, and has a +1 charge. That's highly attractive, but it's going to attract other negatives. This is the only chemical that has an electron deficient H because an H is bonded to an O. These H's here are not. Sulfur is pretty electronegative, but not enough to create an H that can have a little proton sticking out there dangling. So that's why 2-pentanol is the only one to have H bonding. If it has H bonding, okay, of course it has a cloud of electrons, and because it's polar, it has dipolar forces. So the next question, which of the following is the lowest boiling point? Now the lowest boiling point would mean that you have an element who has a vapor pressure that's really high. It evaporates very easily. Elements that resist evaporating, okay, have lower vapor pressures if you look at the same temperature. So something with a low boiling point means it has high vapor pressure, which means the liquids, okay, molecules don't have much attraction for each other and they're able to escape into the gas phase with very little energy. Remember, if this is standard pressure, boiling is when the vapor pressure, the force of liquid molecules, equals the what? Opposing atmospheric pressure. And so the ones that get to this atmospheric line boil lower temperature. Bottom line, this liquid has a low boiling point because it has the weakest intermolecular forces of attraction. So we're asking who has the weakest? Well, looking at our choices, okay, maybe looking at our choices, we're getting there, is this guy has LDFs only. And 1, 2, 3, 4, 5, pentane only has LDFs. Now they all have LDFs, but the ones that are polar, hey, these are polar. They have dipolar forces as well. And this one has also the additional H bonding. So because these are the only two elements, I'm sorry, molecules, okay, that only have LDFs, and they are the weakest force, they can be significant, it's between these two. So the question is, who has stronger LDF forces? Well, you know this is a 4-carbon chain and this is a 5-carbon chain. This molecule we're going to say is more polarizable because it's longer. When this comes in contact with another molecule of its size, same, okay, this cloud of electrons can actually distort more because it's pulling from a longer molecule. So therefore, this has higher LDFs. And this is a less polarizable because it has less carbons, less electrons too, but it's not as long. It's more, if you think about it, it's a little more circular. I know it's not branched, but it's not as long as this one. So this one is more polarizable. So this one has weaker LDF forces, and therefore this has the weakest intermolecular forces here. Therefore, it will boil at the lowest temperature, and that is going to be butane, which is a bute, okay? Bute means 4 carbons. All right, going back and forth is fun. I guess I can see how fun you had the other night. Which of the following molecules can hydrogen bond with water? That's a great question. Now, if you can hydrogen bond with water, it doesn't mean you have an electron deficient It just means that you may just have an exposed what? O, N, or F. All right. So the classic case is who can hydrogen bond with water? Well, if we go back to our choices, good times. All right. Maybe. We're getting there. Clearly, 2-pentanol can hydrogen bond with water because this H, which is electron deficient, which is a positive proton, will attract the oxygen end of water, which is the more electronegative negative end. Okay, so this is a great example, but who else could? Well, all right, this oxygen, okay, is electronegative, so water, the H part of water could H bond with it. So even though it doesn't H bond with itself, it can actually what? Interact with water because the H would H bond. So if this is an H here, and it wouldn't be this far away, but it would attract this negative oxygen and H bond with it. So even though this doesn't H bond with itself because it has no electron deficient H's, remember, carbons and hydrogen share electrons equally. But the negative electronegative oxygen will attract this proton and interact with the water. So 2-pentanone, all right? No, this does not have an O. This does not have an N. This does not have an F for the H of the water to attract to. So this would not. How about this one? We're going to say yes, although the real answer for those that are watching is actually no. These alkyl groups actually get in the way, but based on what we've learned, this is a negative oxygen, although it's not very polar. It could, okay, and we'll consider that for this test, for this quiz. So just based on what I've taught you, not knowing that these will get in the way and make it hard for the water to get in, we'll say that it does interact with the water in H bond. It has a oxygen who's electronegative enough to attract that proton of water. So these two do not H bond with themselves, but they can offer a electronegative element, O, N, or F, to the water to attract to. So it's those three. Okay, so if I go back to my answer, all right, even though the ether doesn't, okay, you get that. So the 2-pentanone definitely, and we'll say this one, but we'll put a little asterisk here in truth, this guy really doesn't, but I'm not making you understand that. Okay. All right, so moving forward, number 7, which of the following can only experience hydrogen bond intermolecular forces with itself? And of course, that's the same as 2-pentanol. It's the only one that has an electron deficient H. So that if this is the rest of the molecule, okay, another 2-pentanol with a what? An O and H, that H can H bond here, and this H can H bond to this O, okay, and H bond with itself. These guys can interact with water, okay, with an asterisk, because they can offer a negative, but they don't have an electron deficient H to bond with themselves. Which of the following molecules has electron deficient H's? That's the same thing as saying who can H bond with themselves, and that's 2-pentanol. Okay, that's just a vocab question. And number 9, in slide 29 of the presentation, there's a graph where the 3 molecules are bucking the trend. All right, so you may pick only as many choices as needed. Let's go to that graph. Okay, I think this is the graph that I was mentioning to. I keep adding new slides to these presentations, so thankfully, hopefully you guys found this to be the right one. So what's bucking the trend is, if you notice, as the period number goes up, as the quantum number n increases, the boiling points increases, and as um, what seems understandable is that the number of electrons in the group is increasing. So these molecules have more electrons, so therefore what's happening is the London dispersion forces are increasing. But then you have a jump through the roof here. And what's jumping through the roof are 3 elements bucking this trend, meaning they're supposed to get lower. If you have a lower number of electrons, for instance, you have tellurium, selenium, and sulfur, and we're going from group 5, row number 5, or quantum number n equals 5, principal engineering level 5, to 4 to 3. The number of electrons in these, notice it's H with S, and with is a row 3 element, row 4 element. As you go down a group, the number of electrons increases. So we expect the lowest number of electrons to have the lowest LDF forces, but these jump through the roof. So these guys are bucking the trend because they H bond. So the reason why the boiling points are so high is they have the strongest attractive forces, which is addition to their polar forces and their what? LDFs. These guys probably have some polar forces, but why they're creeping up is because of the LDFs are increasing as you increase the electrons. And again, we'd expect them to have less electrons, be lower, but in the special case of FON, because of the H bonding, okay, what we have, of course, is the H bonding that increases, in addition to the polar and LDFs, increases the intermolecular forces of attraction incredibly. So what's bucking the trend is H bonding, and H bonding is due to electron deficient H's, okay? So there you go. That's what is choice C. Last one, isopentane is this. Compared with pentane. Now pentane, of course, is a straight chain. You have 5 carbons, so they don't have to scroll up again. Okay, so I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Pentane is not branched, it's isopentane. So compared to these two, hey, they're both hydrocarbons. They only have LDFs. They have the same chemical formula. These are what? C1, 2, 3, 4, 5. C5, H12. They're both C5, H12. If I put the H's in, trust me, there's 12 of them in for every one of these positions here. So they have the same number of electrons, but hey, this shape is less polarizable than the elongated shape. So my friends in chemistry, this is going to have weaker LDF forces. This will have a little bit stronger. So the pentane, not the isopentane. The iso means isomer, same number of stuff, different structure. The pentane, this is isopentane, okay, ane, is going to have a higher boiling point, okay? Now, of course, higher boiling point means that it's going to have a lower vapor pressure. Remember our chart of table H. Liquids that evaporate really easy have high vapor pressure. This is vapor pressure. And of course, when it meets the what? atmospheric pressure, you've got yourself boiling. This is temperature. And so liquids that have a longer, or I say larger boiling point, they boil at higher temperatures because they don't produce the same amount of vapor. They resist vaporizing because they're holding on tightly. This guy has stronger intermolecular forces. Okay, so it's going to have a, so compared to isopentane, compare pentane with isopentane. Compared with pentane, okay, I can do this. Isopentane has, okay, well, it has lower LDFs, it's weaker. So therefore, let's get this red in here. Therefore, it's going to have high vapor pressure. It's going to evaporate and produce a lot of pressure because the molecules evaporate. Okay, and it is going to be less polarizable. It doesn't move electron cloud that much. That's why the LDFs are weaker, and that's why they separate so much easier, and that's why they create a higher pressure upward. And that's why good old number 10, don't know why 13 is there, okay, is the answer. And then make sure I've got this correct. So lower boiling point, that's for sure. Okay, higher vapor pressure, less polarizable. And I put the first one there. Lower boiling point with low vapor, no, it'd be high vapor pressure. Boiling points that are low have high vapor pressure. Lower boiling point, no. So the only one there, low boiling, high vapor, is these two. And of course, the first one is less polarizable. Okay, so I hope that helped.